So today's talk is called The 19th Century Revolution or Evolution. In my last lecture, not surprisingly on the 18th century, we saw the devastating influence of Isaac Newton on British mathematics, holding it back for more than 100 years while great advances were being made on the continent by such great figures as the Bernoulli brothers, Leonhard Euler, and Lagrange and Laplace. One or two people said they felt there was too much emphasis on 18th century activities in Britain rather than the continent, but this was partly because I'm going to redress the balance in my lectures later this year, my 18th century lectures on E and I, and also on Euler, who has his 300th anniversary next year. But also partly because today's lecture also focuses on events on the continent, and in particular in France and Germany. I can't actually cover all the details of 19th century mathematics in 1 hour, so I've just chosen 4 main areas. Some areas I'm leaving out completely. Combinatorics, for example, I mentioned some of the 19th century combinatorics last year. So I'm going to concentrate on algebra, on various types of geometry, on a calculus, and if I have time, I'll also say something about the foundations of mathematics. If I don't, then the foundations will move over to my lecture in 3 weeks' time. But anyway, while you're thinking about that, let's go to France. Because out of the turbulent years of the French Revolution and the rise to power of Napoleon Bonaparte, there were several important developments in mathematics. Napoleon himself was an enthusiast for mathematics and its teaching, and there are even a couple of theorems, a couple of results in geometry known as Napoleon's theorem. I won't go into those today, but I'd like to talk about one of Napoleon's greatest supporters, and this was the geometer Gaspard Monge, who accompanied Napoleon on the Egyptian expedition of 1798. Monge taught at a military school where he studied the properties of lines and planes in three-dimensional geometry, and while he was investigating possible positionings for gun emplacements in a fortress, he greatly improved on the known methods for projecting three-dimensional objects onto a two-dimensional plane, and this subject became known as descriptive geometry. So here you can see Monge, and here you can see the diagram actually from one of his pupils. But so the idea is if you've got a three-dimensional object, how do you represent it in a two-dimensional plane? Well, one important consequence of the French Revolution was Napoleon's founding of the École Normale, and shortly afterwards the École Polytechnique in Paris. Here's the École Polytechnique. And it was here that the country's finest mathematicians taught students. They had really great teachers there. Monge was a major figure at the École Polytechnique, as were Laplace, Lagrange, and Cauchy. And they taught the students who were destined to serve in both military and civilian capacities. They also wrote textbooks, and these textbooks, the textbooks produced at the École, were later to be widely used in France, but also in the United States. They were certainly used, for example, at West Point Academy and other places in the States. The first topic I want to talk about, which actually comes out of this descriptive geometry of Monge, is projective geometry. Because for many 19th century mathematicians, the most basic and important type of geometry was projective geometry, or in other words, the study of perspective. Now, as some of you will know from my earlier lectures, this topic had its origins in early Renaissance painting and had been developed by such practitioners as Brunelleschi and Della Francesca, that you can see here in Italy, and also Albrecht Dürer in Germany. I mean, the basic point is if you have a picture like this picture of Della Francesca, you can see the various lines here which focus on the center. The whole idea of perspective was developed around this time, and you can actually see these how these lines fit in there, focusing one's attention on a particular point in the painting. A number of people like Brunelleschi, Alberti, his student, Della Francesca, they were all involved not only with the use of perspective in their paintings, but also they wrote about it, and Alberti said the first duty of an artist is to know geometry, which of course is the right thing to say. And people studied it theoretically as well. Albrecht Dürer, in earlier lectures I have shown you some of Dürer's drawings, his engravings with perspective, and he also studied this thing theoretically. So here's Dürer on perspective drawing. Don't try this at home. But you can see here, he actually has a grid here, and he's developing ideas of how to draw perspective. In the 16th century, such concerns became the province of practical tradesmen whose crafts involved perspective, such as architects and military engineers, as well as of theoretical mathematicians such as Girard Desargues. Desargues is interesting. I mean, he looks the right character anyway. But he discovered a celebrated result on triangles in perspective. This is a very famous theorem in projective geometry. Basically, you've got a point here, and you've got a triangle here, you've got another triangle here. These are in perspective from this point, in the sense that if you're at that point, you can't tell the difference between A and A dash, B and B dash, and C and C dash. Now, what the theorem says, if you extend corresponding lines, AB and A dash, B dash, you get a point where they meet. If you join up AC and A dash C dash, you get another point, and similarly the other two give you a third point. And what the theorem says is that those 3 points that you get by joining these things up lie in a straight line, that brown line I have here. So that's Desargues' theorem from the early 17th century, that these 3 points of intersection lie in a straight line. It's easier to see why this is true if you think of the diagram in 3 dimensions rather than 2, because if you actually sort of think of these lying in different planes, then the place that those planes meet is along that line, and so you can see why those points lie on the line. Well, after this, projective geometry went underground for about 150 years. Virtually nothing took place. Before emerging with a vengeance around 1800 in post-revolutionary France. And this is where Monge comes back again. Gaspard Monge's skill as a teacher at the New École Polytechnique helped to establish descriptive geometry and also to inspire his talented students. And although his approach was highly practical, he also developed the necessary algebraic machinery to make the subject versatile and rewarding. Now, his most talented student was Jean-Victor Poncelet, who has been called the father of modern projective geometry. Poncelet was actually in jail during Napoleon's invasion of Russia. And what else do you do if you're stuck in a Russian jail? Well, you develop the idea of projective transformations, and you study the properties of figures that remain unchanged under them. So basically what Poncelet was looking at was what geometrical features are preserved if you project things. I mean, for example, supposing you have a bit of glass here with, say, an ellipse on it, and you have sunlight coming down, then you get another ellipse here. But by moving this, you can actually get circles and so on. And in fact, if you start with a triangle, you can get another triangle. Or if you start with a square, you might get a quadrilateral. But the important thing is that whereas in Euclidean geometry you can tell the difference between this triangle and this triangle, as far as this idea of projection is concerned, any 2 triangles are the same. Okay? They're still triangles, so that's one property that's preserved, but you don't actually preserve things like length or angles or things of this kind. So he was concerned with these projective transformations, which actually is a sort of slight generalization. This is actually called an affine transformation. But he was looking at these more general things and studying the properties of figures that remain unchanged by them. This work was much influenced by Monge and Desargues, but also a lot of it was intuitive, unrigorous, and it certainly wasn't well received by the powers that be, the mathematical powers that be in Paris, people like Cauchy. But there was one idea that was truly revolutionary, and this was the idea of duality. This was a real break with the past. In this, supposing you take a conic, say an ellipse, and you take a point not on the conic, and you draw the two tangents, okay? And then you join them up by a line. So given this point, I get a line. In the trade, we call this the pole, and this line is the polar. So you've got a sort of duality between a point and a line. Now the thing is, if this point now moves along another line, then you'll get different lines here, but they'll all pass through the same point. And so, as I say, you get a duality between points lying on lines and lines passing through points. And this was an idea which hadn't been sort of studied before. But essentially what you could get, if you had a theorem, as I say, about points lying on lines, lines passing through points, you could dualize it and get another theorem for free. Okay, you get double value for money if you use duality. And other people sort of took up this idea, in particular Gergon, who was one of the founders of a mathematical journal in France. This was the time that mathematical journals were beginning to get established by Gergon in Paris and Kreller in Germany. And so mathematical and publishing mathematical articles in journals became the thing to do from the early 1800s. Well, Gergon liked this idea of duality, and in 1827 he tried to carry it to its logical conclusion, claiming that points and lines are in some sense interchangeable with the same logical status. Here's one of his results. He starts off, take a plane figure made up of points and lines, and then you can construct another figure. And then in the first one, you might have results about points on a line and lines passing through points and so on. And then within the dual figure, you'll then have a similar situation with lines passing through points. In other words, as I say, you have this duality between lines and points. And so you have a geometry in which any two points determine a line, and any two lines determine a point. Very neat. Even neater than the sort of geometry we're used to. We're used to Euclidean geometry, where if you've got any 2 points, they determine a line. There's exactly one. And if you've got any 2 lines, they determine a point, except when the 2 lines are parallel. And that's an awkward exception. What happens if you take it away? What happens if you look at a geometry where any 2 points determine a line and any 2 lines determine a point? Okay? And if you've got parallel lines, we say they meet at the point at infinity, but the point at infinity is no different from any other point. Here it is. Okay? So we've got a new geometry now. These are the new axioms, and it creates this whole area known as projective geometry. Well, that certainly is something new, revolutionary, but the French mathematicians found they couldn't actually work through the details. It was very complicated. They really didn't quite understand what was going on, even though they sort of invented it. And the scene now moves to Germany with Möbius. Now, I'm sure you've all heard of Möbius. Möbius is mainly known for the Möbius strip, which is a one-sided surface. Here is my scarf, which is in the shape of a Möbius strip. It's not very comfortable, but there we are. This is a one-sided surface, okay? And if you trace around, it's just got one side. And the Möbius strip or Möbius band is named after Möbius, even though he wasn't actually the first to describe it. Anyway, Möbius's appearance here is because he and others in Germany used algebra to attack the problem. You may remember from earlier lectures, with Descartes, a couple of centuries earlier, he was trying to solve a geometrical problem, actually one of someone called Pappus, and in order to solve it, he said, I'm going to let this distance be x, this distance be y, and then he worked out everything to do with the problem in terms of x and y. In other words, he took a geometrical problem and he attacked it with algebra, and then turned it into an algebraic problem. And a similar thing happens here, and so the question is, how do you describe this geometry of perspective? And his idea was to introduce something called the barycentric calculus. And to give you an idea of what the barycentric calculus is, supposing you take your kitchen table and bore 3 holes in it. Again, don't try this at home. And you have a heavy weight here, P, and it's attached by strings through A, B, and C, and you attach weights to A, B, and C. Now, it's quite clear that if you have a heavier weight here, it'll pull P over to that side. If you put a heavier weight here, it'll pull P to that side. And so associated with P, you can give three coordinates, which are these three weights. Okay? So you can describe the position of a point by attaching different weights, and you get three coordinates A, B, and C. And these are quite interesting because, first of all, if I double each of these weights, then the point will stay in the same place. So ABC is the same as any multiple of it. So the point 1, 2, 3 is the same as the point 2, 4, 6, which is the same as the point 10, 20, 30. They are all the same point. So in this geometry, each point has three coordinates, but they're only determined up to multiples. As I say, 1, 2, 3 is the same as 2, 4, 6, and so on. So you're playing this game, and the points are triples of numbers, A, B, C. You don't allow the point 0, 0, 0. And also you can extend the idea, if you think of A being negative, that actually corresponds to points P outside the triangle. You can't do that in practice, but you can actually see how the idea can be extended. So here we have a geometry in which the points have three coordinates determined up to multiples, and also you have, and now for lines it turned out that whereas the normal equation of a line is ax plus by equals c, here the equation of a line would be ax plus by plus cz equals 0. And if you do that, then in fact you get a very consistent geometry, which happens to be the geometry it happens to be projective geometry, the geometry of perspective. And you can see where the duality comes from now, because associated with any point ABC, you associate the line ax plus by plus cz equals 0, and then given this, you can attach a point, and multiples here will give you the same line, and so on. So, I mean, if this is the first time you've seen this, it's a bit mind-blowing, and you obviously probably can't follow the details, but it does actually give a very exciting type of geometry, which is very, very different from any geometry that had been studied beforehand. So the whole area of projective geometry was one invented by the French, developed by German mathematicians, who then attacked it with algebra, and various other German mathematicians developed this, and it became a highly well thought out theory by about 1840. Meanwhile, back in France, there are important. I'll just show you. Sorry. Here is my stamp of a Möbius strip. More examples from my stamp collection, and we're now going to move to algebra, and we're going to move in particular to two people called Abel and Galois. Before I mention them, let's look back at developments in algebra, and I'm going to be looking at the solution of equations. Starting off with, say, quadratic equations. Now, people have been able to solve quadratic equations, or what we now call quadratic equations, since Mesopotamian times, since about 1800 BC. The method that the Mesopotamians, the Babylonians described is essentially one of, you've got a problem, and which we would now recast as a quadratic equation, and they solve it using the idea of completing the square. Well, this idea was later taken up by Islamic scholars, such as Al-Khwarizmi. Al-Khwarizmi, around 850, wrote an algebra book, and this is a book where one word in the title is al-jabra, which gives us the word algebra. Some of you may remember that from an earlier lecture. And what did they do? Well, for a start, since they didn't have negative numbers, or didn't use negative numbers, they actually divided their quadratic equations into 6 types. But let me just take one of these and show you how they would have solved this. So to solve x squared plus 10x equals 39, what Al-Khwarizmi did was he drew a picture. And he said, well, here's a square here of side x, so that area is x squared. I'm going to extend it by a rectangle of side 5 and x. So this is 5x, and same here, 5x. And the reason it's 5 is because 5x plus 5x is the 10x here. And so what we've got is that this shaded area has area 39. That's what this equation says. And now we literally complete the square. How do we complete the square? Well, we just add in this. It has size 5 by 5, so it has area 25. So if you add that in, then you get 64. You get 39 plus 25 is 64. And what you now have is a square of side x plus 5. So x plus 5 squared is 64. X plus 5 is 8. So x is 3. And that solves your problem. As I say, they didn't use negative numbers, so the other root, minus 13, they weren't able to get that way. But certainly this is the way that quadratic equations were solved geometrically. In the 16th century, there were various mathematicians who are now looking at cubic equations. No one had been able to make any progress until 1500, and then various people, including Tartaglia, that some of you may remember, managed to find a method for solving cubic equations. So let me just show you his method for solving a certain type of equation, and I'll go through it quickly, and if you don't follow it, it doesn't matter too much, but I just want to show you the sort of approach that he took. So supposing you wanted to solve this x cubed plus 6x equals 20. And by the way, don't worry about the fact there's no x squared term. If you've got a cubic equation with an x squared term in it, you can always shift things along and get rid of the x squared term. So this is a pretty general type of example. The method that he had to solve these was he tried to find two new numbers. Often if you're trying to solve an equation, you bring in new numbers and you get new equations involving them, and then those are easier things to deal with. And so the standard way that he used to solve equations like this, he brought in two new numbers, u and v, whose difference is this number here, u minus v is 20, and whose product is a third of this number here. Okay? I won't go into the reasons why that he did that I did last year. But essentially, so uv is a third of 6, that's 2 cubed, which is 8. Well, so you've got u minus v is 20, uv is 8. Now this is the sort of simultaneous equations that the Babylonians have been able to solve 2,500 years earlier. Essentially, you put v as u minus 20, shove it in here, and at the end of the day, you'll get a quadratic equation in u, which you can solve, and you get square root of 108 plus 10, as you'd expect, and v is square root of 108 minus 10. And then if you then shove all this back, it turns out that x is the difference of the cube root of this minus the cube root of this. So here's your answer. And this was a sort of general method which Tartaglia explained, and you could solve things like this. What Tartaglia and Cardano and various other people who worked on this didn't explain was how to simplify. This has an even simpler expression. You can rewrite this as 2, and you can check that 2 satisfies this. Unfortunately, Cardano's book on the subject didn't explain how to get from here to here, but this was standard techniques known at the time. They knew how to deal with things like this. The important thing is that so far we've had quadratic equations and cubic equations, and to solve them, all you need to do is to do the arithmetical operations of addition, subtraction, and multiplication, division, and taking of roots. For quadratic equations, you have minus b plus or minus the square root of b squared minus 4ac over 2a. So you have square roots. Here you can see you have square roots again, and you also have cube roots. So you can actually solve quadratic and cubic equations using arithmetical operations and roots. And here's some notes I found the other day, how to solve a quartic equation. And this is how they did this in the 16th century. I'm not going to go through the details, but suppose you have an equation of degree 4. You can also solve this using arithmetical operations and taking roots. And here, for your delectation and delight, is the answer. I hope you're taking notes. But you notice that you're adding and subtracting and things. I hope you're checking this. But you notice it's got square roots, it's got cube roots, it's got fourth roots, it's got all sorts of things. You can actually solve a quartic equation using arithmetic and taking roots. Okay, so that's the history of these things. But the next question is, what about equations of degree 5 or more? Well, this proved to be a lot more difficult, and the search for general solution or formula for these occupy the finest mathematicians such as Descartes and Euler, but little progress was made until along came Lagrange. He attempted the problem, laying the groundwork for the eventual solution. Again, and this is a bit technical, but you don't need to follow the details. Supposing you have a cubic equation, as I say, this is a fairly typical one, you can arrange it for it to be like that. Lagrange says, make this substitution here. Don't worry about the details. The point is that if you substitute x, put this in for x, you get another equation, which looks worse because it's of degree 6. But it's only got y to the 6th, y cubed, and so on. It's actually a quadratic equation in y cubed. And you know how to solve quadratic equations, so you solve that, and that gives you y cubed, and so you can work out what y is. So you get 6 values for y, and that turns out to give you 6 values for x, if you put it back in here. But those 6 values for x is, in fact, just 3 values for x, each occurring twice. And so that gives you your solution of your original equation. Well, so encouraged by his success, he now tried this with quartic equations. So you take a quartic equation. Again, you can arrange that the x cubed term disappears. And you carry out a similar substitution, and you can reduce it to this. Now that, in fact, is a cubic equation. And you know how to solve cubic equations. So you solve that. That gives you a cubic equation in y, which actually gives you 12 different values of x. Well, 12 values for x, but that actually gives you 4 different values, each occurring 3 times. So again, using this reduction idea, you can reduce the degree of your equation, and then you can solve it. So the obvious thing to do is to take an equation of degree 5 and do a similar thing and reduce it to an equation of degree 4. You know how to solve equations of degree 4, or in theory, and then you can solve it. But unfortunately, it didn't work. Lagrange couldn't make it work, and the reasons he couldn't make it work is because it's impossible. But he didn't know that yet. So he took a different approach. And this is the approach that actually got taken up later on by other people. You can see he's not very cheery about the whole thing. So if you're solving this, he said, I'm going to look at permutations of the solutions. You know that if you've got a quadratic equation, you've got x is minus b plus or minus a square root, etc. And so you can go from one to the other. You know, they have the same, they say, have the same form. And so he said, well, let's look at this equation. Supposing it's got 3 solutions, p, q, and r, then I can also write it as x minus p, x minus q, x minus r. These say the same thing. And if you multiply this out, believe me, you can check that the constant term c is just minus pqr. The term in x is just this. The term in x squared is this. And the important thing you notice is that these are all symmetrical in p, q, and r. If I permute p, q, and r, I get exactly the same thing. If I permute p, q, and r, I get exactly no change. Well, he then generalized this idea. He said, well, what happens if I look at other things involving p, q, and r, other expressions, and permute things? If I take pq plus 2r, well, I can interchange p and q. That won't change things. But if I interchange either with r, I get different values coming in. So if I permute p, q, and r, I'm actually going to get 3 different results. 3 values, he called them. Or if I've got something like this, you get 6 different values. And you always get a different number of values, but the number of values you get, the number of different expressions you get, always divides 6. Okay? And in general, if you have a quartic equation, they'll divide 24. If you have an equation of degree n, they'll divide n factorial. And that result was later generalized. In a more general setting, that became what we call Lagrange's theorem for groups. But I'll tell you about groups next time. Anyway, this idea of permuting the solutions and counting up the number of different values actually turned out to be useful. It was taken up by someone called Paolo Ruffini, who said, he made a very bold claim. He wrote a book and said, the algebraic solution of equations of degree greater than 4 is always impossible. Behold, a very important theorem which I believe I am able to assert if I do not err. To present the proof of it is the main reason for publishing this volume. The immortal Lagrange, with his sublime reflections, has provided the basis of my proof. which is so he proved that equations of degree greater than 4 is always impossible. Well, he actually did err, because his proof, well, no one could understand it anyway, for a start. But it now seems as though it contained a gap. And so it was left for others to continue the work. And to cut a long story short, the two people I want to mention, two very tragic cases in the history of mathematics, are Abel and Galois. So it was in the 1820s that a proof did finally emerge. There is no general method, or if you like, no general formula for solving equations of degree 5 or more. If you've got an equation of degree 5, you cannot find a formula which involves just sort of pluses and minuses and things, and taking of roots. But in mathematics, proving that something doesn't exist is a lot harder than proving it does exist, because to prove it does exist, you just produce it. But it was Abel who proved the impossibility of solving the general quintic equation. This doesn't mean that particular ones can't be solved. It's just there's no general method and no general formula. Well, here is Abel, and here is a statue of Abel in the middle of Oslo. He was a Norwegian mathematician, and he proved the impossibility by developing the permuting ideas of Lagrange. But he had a very short and tragic life. He grew up in Norway, but this was way outside the main centers of mathematical life in France and Germany. He was eventually able to spend a little time in both countries, in Paris and Berlin, and he contributed several works to a new mathematical journal founded in Germany by his friend Kreller. And one of these papers in Kreller's journal was his proof of the impossibility of solving the quintic equation. He then returned to Norway, where he contracted tuberculosis and died at the age of only 26. 2 days later, a letter arrived at his home offering him a professorship at Berlin, something he would really have wanted. Well, Abel's work was continued by the brilliant young French mathematician Évariste Galois, he obtained criteria for deciding which quintic and other equations can be solved. And this ultimately led to whole new areas of algebra, now known as group theory. The idea of a normal subgroup, which some of you may have heard of, was actually due to Galois, and also an area called Galois theory, which is also an area of algebra. He also had a short and tragic life. He died in a duel of honor at the age of 20. He was a firebrand who became involved following the July Revolution of 1830. He threatened the life of the Orleanist king Louis Philippe, but was acquitted. But a month later, he appeared on Bastille Day in the uniform of the Band Artillery Guard and carrying several weapons, which didn't please the authorities. He was thrown into jail. He then got into this trouble with this young lady and was challenged to a duel. And the night before the duel, he frantically wrote out his mathematical achievements for posterity. And then, as I say, he got shot in the duel and died at the age of 20. Incidentally, I know someone who's actually writing an opera on this. It would make a wonderful play or radio play. It's the most dramatic life of any mathematician. Because I only told you a small part of it. Anyway, I've got part of the letter that he sent to his friend Chevalier. I mean, people have said that if he'd actually got a decent night's sleep instead of writing out this mathematics, he might have won the duel. But anyway, he wrote, "My dear friend, I've done several things in mathematics analysis. Some concern the theory of equations. In the theory of equations, I have found out in which cases the equations are solvable by radicals. In other words, by square roots and other roots." And so he's actually developed algebraic criteria which tell you when you can solve these things. These days we call it, we mentioned something called the Galois group, named after him. And he said you'll publicly beg Jacobi or Gauss, two great mathematicians of the time, to give their opinion, not of the truth, but of the importance of the theorems. His stuff was really very dense and very difficult to work out, and it was some years before anyone could appreciate exactly what it was all about and what a genius the world had actually lost. I mean, if he'd lived a full life, things would have been far, far more difficult for students studying algebra these days. I want to move on to another topic now. Going back to geometry, you'll remember that you may remember that Euclid's Elements is based on 5 postulates or self-evident truths. And 4 of these are quite straightforward, such as you can draw a circle. Given any center and any distance, you can draw a circle with that point as its center and that distance as its radius. And you can produce a finite straight line continuously in a straight line and so on. But the 5th postulate is very different, and it's much longer, and it says something which looks more like a theorem, something that you ought to be able to prove from these results, hopefully. And it says that if you've got a straight line, the red one, falling on 2 other straight lines, and if the interior angles, these alpha and beta, if they add up to less than 180 degrees, less than 2 right angles, then if you draw these, extend them as far as you like, eventually they'll meet. Okay? So, as I say, you've got 2 lines here, you've got this line here, these add up to less than 2 right angles, 180 degrees. It says that if you draw these, then it'll meet. And Euclid thought that was self-evident, but it certainly has a different flavor from the other ones. And so over the centuries, countless numbers of mathematicians tried to prove it using the other results. And one of the standard ways of doing this was to try and find other results that are equivalent to it, and then to try and prove them. And the most famous one is the so-called parallel postulate, that if you have a line and a point not on the line, then you can find another line parallel to the first one passing through that point. So you've got a line, a point here, you can find another line parallel to this passing through there. And it turns out that if you can prove that, you can deduce this, and if you can prove this, then you can deduce this, and therefore they tried to prove that. And various other people looked at other formulations, which I won't go into now. But the first really significant advance appeared in a book called Euclid Vindicated, written by the Italian Saccheri in 1733. And he considered a geometry in which the parallel postulate is not satisfied. Now, another of the results equivalent to this is that in any triangle, the angles add up to 180 degrees. If you can prove that, you can deduce that, and you can deduce that. So to prove that the angle sum of a triangle is 180 degrees, he looked at 2 cases. First, he said, well, supposing it's greater than 180 degrees. And then we'll suppose it's less than 180 degrees. And let's see if we can eliminate both of those. And he started with this one where the sum of the angles is greater than 180 degrees, and he managed to prove that that's impossible. We get a contradiction. So there's no geometry in which the sum is greater than 180 degrees. And he tried to do the same here, and of course if he succeeded, then he'd have shown that in fact the angle sum is 180 degrees, and therefore we have the 5th postulate. And he thought he proved it, but in fact he was wrong, and he was not able to prove that you couldn't have a triangle where the sum was less than 180. If he had, then as I say, that would have settled the whole issue. And in fact, he was wrong in spectacular fashion. Let's see who we've got next. We've got Gauss, whom I'll come to in a minute. And incidentally, last time I was talking about how he constructed the 17-sided polygon, which you can see there. You thought it was a circle, didn't you? It was a 17-sided polygon. But we come to 2 gentlemen called Bolyai and Lobachevsky, because Saccheri was proved wrong in spectacular fashion, because around 1830, working independently in Russia and Hungary, Lobachevsky and Bolyai were able to construct a geometry in which the angle sum of every triangle is less than 180 degrees. This is a geometry that satisfies the first 4 postulates, but not the last. So you can't deduce the last one from the first 4 if there are geometries where the first 4 are satisfied and the last isn't. So they came up with this, Lobachevsky and Bolyai. It's a very strange geometry. For a start, the angle sum of every triangle is less than 180 degrees. And also, given any line, any point not on it, it isn't the case of having exactly one line parallel to this through here. You have infinitely many lines. The geometry where there are infinitely many lines which are passed through P and are parallel to L. And if you don't like the drawing, well, that's because you can't really draw these things. It's also strange that if you've got any two similar figures, say triangles with the same angles, they must be congruent as well. They must have the same distances, if you like. That's certainly not true in Euclidean geometry. So that's all quite jolly. But the existence of these things was very controversial. Gauss claimed to have constructed one, but of course he hadn't published his results. He never did. In fact, here's a letter saying that another theme I've been involved with for 40 years, I've been thinking about, is the foundations of geometry. I don't think we can establish geometry completely a priori. And I won't get round to it for some time and write up my researches for publication. And perhaps they'll never appear in my lifetime, for I fear the howl of the Boeotians if I speak my opinion out loud. We don't write maths papers like that these days. But anyway, so he was too nervous, even he was too nervous to publish. Meanwhile, Abel was saying, Kreller says that all Gauss writes is gruel, since it's so obscure that it's almost impossible to understand. So if he had published it, we might not have been any the wiser anyway. But, and here, incidentally, is Bolyai. Now, this is interesting, because that's the picture of Lobachevsky, and that's the usual picture of Bolyai, which looks rather the same. And I always felt that if you look like that, you developed a non-Euclidean geometry. But in fact, that was probably Lobachevsky, even though I think they needed a picture of Bolyai, and so they just came up with that one. And recently, this medal has disappeared with a picture of what we believe Bolyai to have looked like, which is very different from that. Anyway, sadly, I should also say, incidentally, that Bolyai's dad, Farkas Bolyai, was a great friend of Gauss and wrote to Gauss talking about his son's great work. And they got this very disappointing letter back. And Gauss said, so you can just imagine the father, full of pride, he spent his own life trying to work on this problem. He tried to discourage his son from doing it, but his son had worked on it and had solved the problem. So he wrote to his friend Gauss, and Gauss replied, if I commence by saying I'm unable to praise this work, you would be surprised. But I cannot say otherwise, because to praise it would be to praise myself. Indeed, the whole contents of the work, the path taken by your son, the results to which he's led, coincide almost entirely with my meditations, which have occupied my mind partly for the last 30 or 35 years, which of course he never bothered to publish. And as you can imagine, the Bolyais never forgave Gauss for that. And sadly, Bolyai and Lobachevsky, living in Hungary and Russia and not in the mainstream of mathematics in France and Germany, they never enjoyed the credit that was due to him for their spectacular discovery. In the meanwhile, other things happened. Geometry. Oh, incidentally, here is another view of what, this is due to Poincaré, of a non-Euclidean geometry. Now, here's a geometry where you're inside the circle, and you've got various lines and so on, and some of the lines meet, and you can talk about triangles and things, and then you've got lines being at right angles if they meet on the boundary, and you've got various other things from this picture. This is a picture, incidentally, that Escher used quite a lot in his drawings. And you can actually interpret all the geometrical terms like point, line, right angle, and all these other things in the context of this. And this is a much more down-to-earth version of what this strange geometry looks like. Well, geometry then continued, but it was rather a mess because the mathematician Riemann, some of you will know of the Riemann hypothesis, Riemann generalized the ideas of distance and various other things in the 1850s, and using them, he managed to obtain infinitely many different geometries, all non-Euclidean, each one equally valid, and each one a candidate for the world we live in. And indeed, it was one of Riemann's geometries, rather than Euclidean geometry, that proved to be the natural setting for Einstein's theory of relativity many years after Riemann's death. So this was a real revolution of the way we think about the world around us. In 1800, we thought we were Euclidean, and by the 1860s, there are infinitely many competing geometries, and we didn't know which one it was. So it had become very, 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 very confusing. And the rest of the years of the century, they saw many attempts to sort out the mess. There was one contribution by Felix Klein, a German mathematician, who tried to express it algebraically in terms of collections of these transformations we're talking about. And it wasn't until the end of the century that David Hilbert decided to go right back to first principles. Even Euclid was found to be a bit fishy in various places, and David Hilbert wrote The Foundations of Geometry, where he completely treated all the geometries around from an axiomatic point of view. Euclidean geometry, projective geometry. By this time, it had been found by Klein that all the geometries are actually hidden in projective geometry, that's possibly the most natural one. And Hilbert basically then sorted out. So it's very, very interesting. You start off in 1800 with just one geometry. By the middle of the century, you got a huge number of competing ones, infinitely many competing ones, and then finally they were all sorted out, sort of, in the second half of the 19th century. Well, I think that's the last I'll say about geometry in this lecture, but I'd like now to go to look at some what we call analysis or calculus. Some of you will remember from earlier lectures, and I'm not going to go through this, but I was talking about Newton's calculus, and some of you may remember. Basically, in Newton's calculus, if you try to find the slope of a line, he brought in this small quantity called O, and at this stage he cancelled it, he divided by it. And then at this stage he ignored it. You don't need to know any more than that. The point is that this was very iffy, because at one stage, if he's cancelling it, it means it can't be zero. And if he's ignoring it, it says it is zero. And this was sort of taken up, as I mentioned last time, by Bishop Berkeley, who was very worried about the inconsistencies in Newton and Leibniz's geometries. How could they sort it out? It became increasingly important to sort it out, because all sorts of strange things were happening in the whole area, and it needed to be put on a firm ground. And there were two people who contributed to this, and one was Bolzano and the other was Cauchy. So let's see where we are. There's Bolzano. In 1817, Bolzano produced a pamphlet that actually, which, as it says here, gives a purely analytical proof of the theorem that between any two values that give a result of opposite sign, there's at least one root of the equation. What on earth does that mean? Well, it means that if you've got a graph like this, okay, and here it's below the axis, and here it's above the axis, and it's a continuous line, then somewhere in between, it must cross the axis. If you're going to get from here to here without lifting your pencil from the paper, then somewhere or other you've got to cross the axis. Well, this is intuitively obvious, but why is it true? And Bolzano was the one that sort of really explained for the first time and proved it rigorously. And this was really the first attempt at rigorous calculus. Unfortunately, Bolzano lived in Prague, and like Abel, this was way away from the mainstream of mathematical activity. His work was largely ignored. Before I say what did happen, here's another example that if you look at x squared minus 2, then when x is 0, you get minus 2, which is below the axis, and when x is 2, you get 2 up here. So starting here and starting here, you actually cross the axis at some point. And where do you cross the axis? Well, it means there's a point where x squared minus 2 is equal to 0. So this is the point, the square root of 2. So this theorem says that the square root of root 2 exists. This is where it is. Okay, well, we'll come back to that. So the next person that and he is really the most important figure in this story. This is Cauchy, born in the year of the French Revolution. And he had been looking at these problems caused by this dividing by a number which is not 0 and then putting it equal to 0. And he decided the best way of dealing with this was actually to introduce the idea of a limit, something that tends to zero, but never quite makes it. And that's the approach we use now. And in his book of 1821, called Analyse, he introduced the idea of a limit, and using this idea of a limit, which as I say is what we use now, he was able to explain exactly what it means for a curve to be continuous. In other words, for you to be able to draw it without lifting your pencil from the paper. Exactly what it means, what the slope of a curve is. That was one of the problems of the calculus. And the integral, how big something is, the area. And he was able to explain all of these things properly. And here is the crucial word, limit. What this says is when the values successively attributed to the same variable approach a fixed value indefinitely in such a way as to end up by differing it from as little as we could wish, this last value is called the limit. And this is the crucial word, if you like, in 19th century calculus, the use of the word limit. And as the century progressed, Cauchy's ideas were developed by other people, and they were also stretched to the limit, one might say, as various very awkward curves were discovered that needed very careful studies, things that you could not study with the rather hand-wavy ad hoc methods that had been used before. It was crucial that Cauchy's ideas, as developed by others, rigorized the whole subject. And I'd like to illustrate this by showing you a curve which is actually continuous everywhere. In other words, it's joined up. But it has no... So it's got no jumps. But also, it's what we call differentiable everywhere. It's differentiable nowhere. It's got corners everywhere. So think of something all joined up, but it's got corners everywhere. And this is the so-called Blancmange function, as we call it now. And you can see it, there it is. It looks a little bit like a blancmange. We did an Open University television program on this, and we coloured it pink. But, although correctly it should be white, of course. But you start off with a sawtooth like this, and then you take two semi-sawtooths, and you add them to this, and then you get this shape here. And then you take some smaller ones, and you add those, and smaller ones still, and you carry on and you do this forever. And if you do this forever, you get this thing here. And I mean, here you can see something that has a corner here. Okay, and here you've also got corners there, you've got corners there. You've got more and more corners coming in at each stage of the process. And then in the limit, you've got corners everywhere, and yet it's still all joined up. So it's a very, very strange curve. As I say, it's often called the Blancmange function because it looks like a pudding. Ian Stewart once described the Blancmange function as a trifle unorthodox. So I was quite happy to take that joke over from him. Right. Well, I'd like to end up by talking a bit about numbers and how do we actually define a number? Well, we're used to some numbers. We're used to the natural numbers, 1, 2, 3, 4, 5. I hope so, anyway. And that worked for thousands of years, but eventually you got new numbers coming in, like 0 and the negative numbers. It was quite a long haul to get from here to here, but eventually, as I say, you had these negative numbers coming in, and so we get the integers, as we call them. And you can also look at fractions, which we call rational numbers. You've got 5 over 7 and 11 over 3 minus 1 over 7, and that looks pretty straightforward. You just got by taking one integer and dividing it by another. Oh, be careful, don't divide by 0. And you can also arrange that the number at the bottom is one of these things. And so that's nice and easy. Or is it? You've got a half, okay? You've got 2 over 4, 3 over 6, 10 over 20. They're all different fractions, but they're all the same number. So you've actually got to work through that. And in fact, if you're doing a sum like, if you want to work out a half plus a third, well, I don't know how to do that. So what I do is I replace the half by 3 over 6, the third by 2 over 6. Or I can add 3 over 6 and 2 over 6. That's 5 over 6. But you can see sometimes we don't want to use a half and a third. We sometimes want to use the other versions of it. in some calculations, it's more convenient to use 2 over 6, for example. So even the rational numbers are not quite as easy as we think. And the next question is, how about real numbers? You've got the number line, the x-axis. What are all those points? Well, that's easy. You just take all the rational numbers, and then you add the irrational numbers. But what is an irrational number? It's a number that's not rational. So how do you... So what is a number? What is a real number? And this was a big problem that mathematicians had in the second half of the 19th century. What is a number? We know what the rationals are. We think we know what the reals are, but what are they? We've got all these extra numbers, like root 2 and pi and so on, which can't be written as fractions, but what are they? And this is completely independent of complex numbers involving the square root of -1, which I'll come to later in the year. But even looking at these, we still don't know how to explain what a real number is without saying, well, it's a rational or an irrational, and what's an irrational. We can look a bit more about these, and I don't know whether you've thought about these things. I mean, some rational numbers you can write as decimals, finite decimals, 0.75. Some go on forever. A third is 0.33333, and so on. Some recur. Here, 2/7 is 285714, and then that comes again, 285714, 285. But you can actually see that it actually recurs. If you add them all together, you get a much more complicated fraction, but again, eventually, it recurs. And so after a bit of playing around, you're led to believe that every rational number has a finite or recurring decimal. You might like to think about why that is. And also it works out the other way around, that if you have a finite or recurring decimal, you can always write that as a fraction. I mean, an example of that is supposing you had this recurring thing here. If you multiply it by 100, you get 24 point... how do you write this as a fraction? You multiply it by 100, so you get 24 dot point all of this. If you subtract upwards, you get 99x's, all this bit goes, 99x is 24, and so x is indeed a fraction. And you can always do that. Given any recurring decimal, you can always write as a fraction. So it's quite clear what you've got to do there. You actually define what is a number. If it's a fraction, if it's a rational number, then it's a finite or recurring decimal. And if not, then it's got a non-recurring decimal. So we can actually define a real number as an infinite decimal. So we actually define root 2 to be 1.414213. This doesn't recur. The one for pi doesn't recur. And we say all the rational numbers are recurring decimals, and all the other numbers are ones that don't recur. And that seems to solve the problem until we start to do calculations. Because if you define the square root of 2 to be this, how do you prove that this is equal to this? Because what you've got to do is you've got to write that as infinite strings and start to multiply them together. And if you're multiplying them together, you've got to start at the other end. And the other end is a rather long way away, and you really can't. So you're in trouble again. And this is, again, this seemed to be the right way of doing it, using infinite decimals, and sadly, it didn't work. Well, I'd just like to end up by sort of saying how it was solved. There were two things that occurred. One was Dedekind, and he came up with a way of defining the real numbers. And the other person involved was Cantor, who had some interesting arguments, which I'll save for next time, basically about sets and the fact that some sets are bigger than others, and some infinite sets. The idea is there are some infinite sets that are bigger than others, which I'll talk about next time. But let me end by telling you about how Dedekind got around this problem about how to define a number. And he introduced the idea of what we now call the Dedekind cut. And basically the idea is that if you have the real line with all the numbers, and if you just have the fractions, the rational numbers, if you just draw all rational numbers, a lot of them, there are gaps. And what are the gaps? The gaps are all the irrational numbers that go in the middle. So the aim is to fill the gaps with numbers, and these are numbers like root 2 and pi, which you can't write as a fraction. And Dedekind said that each gap is a number. And you define it by, you look at all the rationals less than it and all the numbers greater than it. So for example, if you've got the square root of 2, how would you define the square root of 2? You look at two sets of numbers. These are all the rationals less than the square root of 2. In other words, all the numbers whose square is less, all the positive numbers whose square is less than 2. And you look at all the rationals which are greater than the square root of 2. And you can see that here you have one set, here you have another set, and you define this as this pair of sets. Okay? So this is called a Dedekind cut. You cut the line in the middle, and the place you cut it, this is where the number goes. So a Dedekind cut basically consists of two sets of numbers. All those on this side are less than everything here, and they will define a number, and this number is the thing that appears in the gap. And so that's how you define all the numbers. That's very, very different from what you've learned at school and how we define numbers, but as I say, one had to go through all that actually to work out what a real number is. And there are many other ways of defining them, but that is the way that first arose, really, in the 1870s. So I think I'll stop there, and thank you very much for coming.